Imagine the Alaskan woods in the middle of winter. The temperature regularly drops to 40 degrees below zero. For almost every animal on Earth, the rules here are absolute. Stay liquid, keep the ice out of your body, and you survive. When water freezes inside a living cell, it forms sharp ice crystals that act like tiny knives. They slice through delicate cell membranes, causing permanent and lethal damage. The Alaskan wood frog ignores this rule. Instead of fighting the cold, it invites the ice in. It lets itself freeze. It spends the winter under a thin blanket of leaves, barely hidden from the air. Up to 70. It listens for the first physical touch of an ice crystal on its skin. That contact acts as a starting gun for an emergency plan that unfolds within minutes. The liver immediately begins ripping apart its stored fuel, glycogen, and floods the bloodstream with glucose. This isn't a subtle rise. The frog's blood sugar levels shoot up to 10 times their normal concentration. Simultaneously, the frog's kidneys shut down. Instead of filtering out waste, the frog begins hoarding urea, allowing it to build up in every tissue alongside the sugar. In any other animal, this flood of sugar and waste would be toxic. In the wood frog, these chemicals form the foundation of a precisely coordinated preservation system. This glucose doesn't actually stop the frog from freezing. Its real function is more targeted. It controls the physical location where the ice is allowed to form. As ice forms between cells, it pulls liquid water out. The cell shrinks like a dehydrated water balloon. However, high concentrations of glucose and urea packed inside hold enough water to prevent collapse. The ice stays outside, while the inside remains a liquid island. The frog prepares for this state during the autumn. As nights dip below freezing, the frog undergoes up to 15 shallow freeze-thaw cycles. Each cycle allows the liver to stockpile more life-saving glucose before the deep freeze of midwinter arrives. This survival method relies on a spatial trick, surrendering the outer fluids to the cold while using chemistry to keep the internal cell structure intact. The most dangerous moment isn't the freeze, but the thaw. If the outside of the frog warmed up before the internal organs were ready, the system would break down and the frog would die. Because the glucose was distributed equally through every tissue during the freeze, the frog thaws symmetrically. The inside and outside wake up at the exact same rate, allowing the cells to plump back up as liquid water flows back in. Once the ice is gone, the biological restart is nearly instantaneous. The heart gives a beat, then another. Within hours, the lungs draw breath, and the frog is fully functional again. This state of chemical equilibrium is what allows the frog to flatline through the winter and return to life in the spring. This process has direct implications for human medicine. When a donor organ is prepared for transplant, doctors are fighting a brutal biological clock. A human heart or liver outside the body starts to break down in just a few hours. This short window limits how far an organ can travel. Every year, thousands of viable organs are lost, simply because they could not reach a patient before the tissue degraded. Researchers are now applying the wood frog system to mammalian tissue. By flooding organs with similar sugar concentrations to dictate where ice forms, they have begun successfully freezing and thawing donor organs. This chart shows the impact of these techniques. Using the frog's chemical method, scientists have successfully preserved rat livers for 4 days and pig kidneys for more than 10 days. By surrendering to the cold, the Alaskan wood frog utilizes a chemical adaptation that is now being used to rethink how we preserve human life. Extending the preservation of donor tissue from a few hours to several days could save thousands of lives.